actually used by our companies, and some more advanced topics. So just some quick intros. First about me, I'm Aditya. I'm currently a software engineer at Google Cloud, where I work on virtual I/O and SSDs. I'm a recent Carnegie Mellon and Cal graduate. And if you want to contact me about cloud computing or working for Google, that's my email. Feel free to reach out.
Hi, I'm Patrick. I've been in the software engineering business for 15, 17, I don't know, a lot of years. I started at Google back in the mid-aughts, and I did a healthcare data startup, Nuna.com, for a while, and now I'm at Coda.io making really fancy documents. I live in San Francisco, and this is my email address.
Okay, so the first thing that we're going to start with is just defining some basic terms that we'll keep referring back to in the lecture. And you may be familiar with some of these, but this will just kind of help us get us all on the same page because we'll keep using these terms a lot. So first, the most basic example is a recursive function is just the act of an algorithm calling itself. If you want a fun little Easter egg, you can type recursion into Google search, and it will keep referring you back to the search result for recursion. So this is contrasted with iteration, and iterations is the types of functions that you're already familiar with, where they use some sort of built-in loop to repeat, like a while loop or a for loop. So on the right-hand side here is an example of a recursive function. Foo of n is calling foo with the argument of n+1. Now, why does recursion work? So we're going to go very, very briefly into computer memory and talk about frames. And a frame is the piece of memory where a call to a function runs on your operating system. So when you call a function as part of a program, there will exist a frame that will contain the pieces of information that is needed to run that function that will exist somewhere within your computer memory. So on the right-hand side here, you can see when the first call to foo was made, there was a little piece of memory allocated that says what this function is and what the argument that is used for the function, so that it was actually able to be executed. And this will happen for any function that runs as part of your computer memory. And we'll also be referring to the call stack, or the stack as some people call it. And this is not the same as, or it's similar to the data structure stack that you might be familiar with, but this is an internal structure that basically contains the frames of currently running functions. So the way you can think about it is your operating system creates a stack data structure, and whenever you call a function, it will add that function's frame onto the top of the stack, and when that function returns, it's removed. So the operating system is doing with functions what you might do with integers or any other value that you would put onto a local stack data structure. So here we can see that foo with the argument n ends up calling foo with the argument n+1. And this frame right here is now the current frame of the stack. And when it returns, this will be the current frame of the stack. So it just pushes and pops like a normal stack that you'd be familiar with. Right, so yeah, when it returns, this is the current frame. So why do we even need to learn recursion? You already know how to do a for loop, and most of the time you'll probably be writing functions that utilize loops. The main advantage of recursion is that we can break down difficult problems into much easier subproblems. And for a lot of organizations, especially smaller organizations, developer time is more scarce than computational resources. So being able to write a very simple, like a few lines of codes change to a complicated problem allows it to be easily reviewed and then deployed faster, which will help a lot. There are certain applications in which recursion is faster. An example is quicksort, where you would be using a stack data structure anyway. So here, since instead of us allocating a stack, we're just going to use the OS's built-in stack for our functions. Recursion requires fewer mutable variables. So normally when you define a loop, like a while loop, you'll define it as a condition like while I is greater than 0. And then within your loop, you would do something like a decrement, I minus equals 1, right? I is a mutable variable. And there are certain applications, such as compilers, that are not able to utilize mutable variables. So if you want to have some sort of looping pattern, you are required to use recursion for that example. But the real reason that we're talking about recursion is it comes up a lot in interviews. It is probably overrepresented in interviews compared to actual work. So it's really good to understand it, and it will help you not just solve recursive problems, but also more advanced interview problems down the road. And then finally, the disadvantage of recursion is there's only really one disadvantage, is that it's pretty space inefficient compared to iteration. And it's a significant disadvantage, which is why for a lot of real world use cases, we'd prefer an iterative solution. So to get you all thinking recursively, let's just look at an example from high school math that you probably would be familiar with, which is factorials. The factorial is a number written with this exclamation point at the end. And that is just the cumulative product of that number from 1 up into that number, right? So 4 factorial is just 1 times 2 times 3 times 4. And then 5 factorial is the same. It's 1 times 2 times 3 times 4 times 5. So I'm sure you've noticed the pattern here is the factorial of 5 is just the same as the factorial of 4 multiplied by 5. And this will hold true for any positive value, where the factorial of n is the factorial of the previous number multiplied by the current number. But this definition that we have here in the last line isn't entirely correct. Does anyone know why it's not entirely correct? You can just speak up or put it in chat. Or
there's like no base cases, so the factorial is going. I mean, the implementation factorial will be like, I guess, infinite recursive.
Right. Yes. So that's exactly right. The factorials, there's no such thing as a negative factorial, right? And the way that we define this is it will just recurse infinitely. We'll never hit a base case to stop. And if we try to actually run this on a computer, we'd keep adding frames and frames to our stack until eventually we just run out of memory. And when this happens, this is called a stack overflow. So if you've ever used the Stack Overflow website and you're wondering where that name comes from, it's this phenomenon where we just end up using so much computer memory, normally from not hitting a base case, that our stack just runs out of room and our computer is like, you can't run this function. So for factorials, the base case is pretty obvious. We don't want a negative factorial. So if n is 0, we're going to 0 factorial is 1. So we're going to return 1 in that case. 1 factorial is also equal 1. So we can include that in the base case as well, because it'll save us a little bit of memory. Other than that, for all other positive integers, we'll define the factorial the way that we defined it previously, with the factorial of the current number being equal to the current number multiplied by the factorial of the previous number. And base cases are the entire reason that recursion works. When we're thinking about recursion, we want to make sure that we actually hit a base case. Otherwise, we'll just end up computing infinitely, and we'll either just make your operating system really mad, or if you're using some sort of virtual memory system, you could just end up using a lot of your organization's money, which will be pretty bad. So here is an example in Python of how we would define this. We'd check if n is in the set of 0 and 1, and if it is, we'll return 1. Other than that, we'll return factorial of n minus 1 times n. It's pretty straightforward function definition. So here's the interesting part. Does anyone know what the time and space complexity of this recursive function is? Actually, can't see chat, so Patrick, if there's anyone saying anything on chat, just would be.
Oh, sorry. Yeah, I think it would be like n factorial for the time complexity. For the space complexity, I'm not sure.
Okay, so you're saying n factorial and unsure for space complexity. Okay.
Right.
So what this actually turns out to be is it's linear for both time and space complexity. And the reason that it is linear for both time and space complexity is there is just a single operation for each positive integer. And that operation is the multiplication step of that we're doing here, right? So for factorial of 5, the only new information that factorial of 5 is doing compared to factorial of 4 is this single multiplication step here. And that will be true for any number up to n. So that's how the time complexity is. For space, it's also linear in time complexity because the only space being allocated for each function, you see in this function, we don't allocate any additional data structures or any variable lists or arrays or anything. The only thing that we're doing is we're calling a function. And as we explained before, when you call a function, your operating system intrinsically allocates space on the call stack. So for each integer, it's just allocating the space for its frame, right? So factorial of 5 has its space where factorial of 5 will run, and it will call factorial of 4, and factorial of 4 will run there. And that's the only memory that is being used. So for both time and space complexity, this is linear. So this is the iterative example where we would use a loop. And does anyone know what the time and space complexity would be for the iterative example compared to the recursive example?
So there's a chat. Anjali says space would be O of 1, so constant.
Yeah, that's exactly right. So the difference here for the iterative version is we created a mutable variable, and a mutable variable is base. So instead of storing intermediate computations in stack frames like we did in the recursive version, we created a variable called base that stores our intermediate computation. So regardless of whatever number we put in for n, the only memory that's going to be used is a memory used for base here. So that's why it'll be constant space. And time complexity is the same because we still have to do the multiply operation that we were doing before. Cool. Yeah, so no surprise, mathematical sequences are a common situation in which recursion occurs. Another one you might be familiar with is the Fibonacci sequence. And this is basically a sequence where the next integer in the sequence is just the sum of the previous two integers in the sequence. And so the sequence starts out with 0 and 1, and then the next one is 0 plus 1 is equal to 1, and then 1 plus 1 is equal to 2, and so on and so on. And this, I'm sure you've seen the images on the internet with the spirals and like the golden ratio. So this is the sequence that derives that. Okay, so go ahead and put, you can use Python or any language that you would think. Just go ahead and like type into chat how you would think the Fibonacci, how we would code up Fibonacci. And you can assume non-negative. So I'll give you a little bit of time to type this up.
Gotta love some extra clout.
Yeah, clout is eternal, so.
There you go.
Patrick, is about everyone done typing in the chat?
We've got one complete function in the chat now.
Okay. Give everyone a little bit more time.
Hey, Amy says same thing, but in Java. I love it.
Yeah, feel free to use whatever language you're comfortable with. We're going to use Python because it's pretty, its syntax makes it pretty short, but pretty much every company will let you use whatever language you're comfortable with, as long as they can find someone who can read that language. So don't do like Lisp or anything, but you can use Java. All right, let's move on. Let's see what you all came up with. So no surprise, the solution is pretty similar to what we saw for factorial. Our base case is for 0 and 1. The first two numbers of a sequence is that they return themselves. And then for every other number, the operation that we're doing is we just do the sum of the previous two numbers, right? So this is the there's only, so this is the additional operation that we're doing for the current Fibonacci number. Now, looking at this, is anyone able to tell me what the big O time complexity is of Fibonacci? This is a little more challenging than factorial, so it's okay if you.
We have a answer. Anjali says 2 to the n.
Okay, yeah, that's 2 to the n is the answer that would be accepted in interviews. And if you're not clear why it's 2 to the n, it makes more sense to actually draw out Fibonacci. So a call to a Fibonacci number is actually producing 2 separate branching sequences. So this call for Fibonacci of 5 here is producing a call from f of 4 and f of 3. But f of 4 produces its own call to f of 3. And these go down totally separate branching chains. And so it ends up with this pattern where each call to a Fibonacci state ends up generating 2 other states. And these trees aren't exactly balanced. So the actual answer comes out to be 1.61 to the n, which is the golden ratio. But no interviewer is going to expect you to know that. 2 to the n is a perfectly valid interview answer. Is everyone clear on why that is? All right.
Yes, they are.
Cool. So let's dive into an interview question. This is, I think I've actually seen someone use this interview question here, but it's a pretty good example of how we can use recursion to break down a more complicated problem. So the problem statement is pretty simple. Given a binary tree, check whether it is symmetric. And for symmetry, we're going to define the tree being a mirror of itself, right? So if we cut a line down this slide, and we were able to actually like fold it in half, we could see that this tree is would fold exactly, right? This 4 would fold onto this 4, this 3 would fold onto this tree right there. And keep in mind, this is a binary tree. So we're only expecting up to 2 children per each node in the tree. So just here's some examples in order to make this more clear. So here we can see that the tree is not symmetric because the outermost nodes here, 3 and 5, if we were to fold the tree, they would fold onto each other and they wouldn't match. So that would be a mismatch. And then here, these subtrees are identical. Let me actually do this. Yeah. So here, 3 and 4 are identical. Wait, hold on. Did I skip a slide? Okay, whatever. I think you guys get the point. You know what symmetry is. Let's actually think about this in terms of a function. So what are the conditions that should be true for a tree to be symmetric? And secondly, what should be our base case? And the way you should think about a base case is, what is the appropriate time to stop recursion? So for symmetry, the way we can think about symmetry for a tree is it fundamentally is just a matching problem, right? If we think of the most basic example of like a tree, right? It's just a pair of root nodes. So their root nodes have to be identical. And then let's add children to both of those root nodes, right? So now, instead of just having a root node, we have 2 trees that have 1 root and then 2 children each. For symmetry to be achieved, the left subtree of the left tree and the right subtree of the right tree have to be identical, right? So those two nodes have to match. And then the right subtree of the left tree and the left subtree of the right tree have to be mirror images. So they have to match. So it's essentially just a matching problem, and we have to figure out what nodes we actually want to compare. That is how we would think about this in a recursive solution. And so then the base case of when we should stop recursing is we've run out of nodes, right? The tree doesn't have any more children. And so at that point, we can stop recursing and then return up whatever value we want to return up. So let's look at some pseudocode here. We're going to define this in Python. So I hope you're all able to follow along here. Let me look at my notes to check where we are on time. Okay, we're good. Okay, so here's the tree node class on the right, just so we're all on the same page of what a tree node looks like. And it's just a value, and it contains a left tree node child member and a right tree node child member. And you probably noticed that tree node itself is a recursively defined class, right? A tree node points to other tree node members. So this is an example of how you can kind of like figure out that recursion makes sense to use in this use case. And so like anytime you see a class like that, like maybe like a linked list that's defined as like a pointer to another pointer, think if there's a recursive solution that might work there. So if we look at this pseudocode, the way that we're actually going to define this is we'll just look at this isMirror function right here. And we're going to start out with two roots, the roots of our two trees. So if there's a base case, we're going to return true, right? We've decided we want to stop recursing, and we're just going to return true at that moment. And then secondly, if there are still root values to check, we're going to do two steps. We're going to first check if there is symmetry, and then we're going to perform a recursive step. If none of these, if we don't hit the base case or we don't hit the recursive step, then that means we're going to return false, because we haven't reached a solution, or we haven't reached a situation where we think that we need to recurse further. So does anyone have any ideas of what just the base case would be?
We do have a chat saying the base case is when the node is a leaf.
The node is a leaf.
Yeah, I mean, the
That's-
node is a leaf, meaning that it doesn't have any children. So
Okay. Yeah. So that's not incorrect. We could define it as if the node is a leaf, but we are actually going to define it as if the nodes are none. And the reason for that is it's just simpler pseudocode here, where if they're both none, we're going to return true, and we'll just do all the symmetry checking in one step, as opposed to symmetry checking here and symmetry checking here. But that's a totally valid solution. You're not going to be penalized for having your base case be leaves if you try to present this in an actual interview. This is just how we defined it here so that our pseudocode looks a little bit simpler. So from that, does anyone have an idea of what the check symmetry step of this function would look like?
yeah, so if I remember correctly, you say in the previous slides that we have to make sure that like the left subtree of the left tree has to be equal to the right subtree of the right tree. And then also like the right subtree of the left tree has to be equal to, I think, the left subtree of the right tree. That's what I remember.
Right, that is a correct example. But the problem with that is, how would we check that a subtree is equal to another subtree in one step?
Right, you have to like to do some recursion in that step, but we are doing it later on, so.
Right.
Mhm.
So the way we're going to think about this is, we're going to check for symmetry in a case where it doesn't make sense to recurse anymore. Right, and you brought up the example of being leaves earlier. That's a case where it doesn't make sense to recurse anymore. So that would just be, you would check the value of the two roots, right? You would just check, is this value equal to another value? And this will be the same if the current node that we're looking at is both a leaf and not a leaf. And do you understand why it will be the same? Because we'll just check on one level of the tree at a time, right? We're not checking the entire descendants of the tree. We're just checking two specific points that we have determined will fold onto each other. So if we just have two roots, it's just the two roots. If we have some children, this could be, for example, like the leftmost node and the rightmost node. We've determined they fold onto each other. We're just going to check those two values and see if they're equal. So once we've done that, we're reaching the actual difficult part of this question, which is, how are we going to apply this step recursively? And so a much easier way to think about this is to think about what this will look like when checking for identical subtrees. And once you figured out what this step looks like for an identical subtree, you can reverse the order of arguments in order to check for mirroring. Because what mirroring is, what makes mirroring different from just being identical, is instead of checking that the leftmost subtree is equal to, of one node is equal to the leftmost subtree of the other node, we're checking the leftmost subtree of the first node is equal to the rightmost subtree of the second node. So does anyone have any ideas on what the recursive step for this will look like?
We've got an answer posted. Is mirror root 1 dot left, comma root 2 dot right? Excuse me. And is mirror root 1 dot right, comma root 2 dot left?
Awesome. Okay, that is exactly right. And if you're not clear why this is correct, what we are doing here is we're basically swapping the ordering in order to make sure that the nodes we want for this equality step are compared to each other, right? So if we look at this very simple example, where we have this three as our leftmost, and then this three as our rightmost. When we are at when we're at this step, where we have these two nodes, right? We want to make sure this node is compared to this node here. And in order to do that, we make sure this node recurses down to its left child, and this node recurses down to its right child. And this is the same for both the inner nodes as well. We want the leftmost node to recurse down to its right child, and then the rightmost node to recurse down to its left child. And this property will work for arbitrarily complex binary trees. So we can just keep adding children, and as long as we keep flipping the order of arguments, we'll end up actually being able to check for symmetry. So I hope that's clear for everyone. This is an example of like an actual interview question you may encounter. And it's something you can build up from in steps. So like how we built up from the base case here, and then we were able to figure out just the check for symmetry step, and then a recursive step for identical trees, and then a recursive step for symmetric trees. Following that pattern in interviews is not only totally valid, it's actually beneficial to your interviewer because it shows that you're able to think critically and break down these complex problems and apply the techniques that you're learning here. So I'm gonna stop presenting now and actually hand this over to Patrick.
Okay.
Let me stop sharing.
Yeah, thank you so much, Aditya. That was awesome.
Yeah, I hope it helped.
Let me just see if I am able to. Okay, I think I'll be able to see the chat at the same time. Just expand. Okay, great. Oh, no. There we go. Okay, so let's do some more interview examples. Here we are going to sanitize some sensitive data out of an object. So we're going to work on a JSON object. I'm guessing most people have dealt with JSON, but it's JavaScript object notation. It is anything, basically anything that could be in a JavaScript object, just it's a way of serializing it into text. So we're dealing with integers, strings, but also arrays, objects. Here's an example of what that would look like. And what we want to do for sanitizing it is, say we're looking for a sensitive string, like a password, and we want to remove it from the JSON object that we get. So here's our function definition we are told to implement, sanitize object, getting the object password and the string to replace the password with. So an example of what the desired output would be, we are going to replace the word corgi, because corgi is a very sensitive password. That could be the whole string, could be in the middle of a string, it could be in an object, it could be in an object inside of an array, it could be just an array of strings, could be lots of things. So before we even get to the recursion part of this though, there's a tricky, well, something that's not always the same in different programming languages that you should probably watch out for is exactly how to do the detail of string replacement. Because some languages, like all languages basically have some sort of string replace function, but does it mutate the string, or does it leave it alone and return you a new string? So that's the kind of detail where like paying attention to that kind of detail can be a good thing to do in interviews to show that you really do understand the language you're working with. Because so for example, JavaScript strings are immutable. You cannot change them in place. You have to reassign the key in the object you're dealing with to the new string with the replacement. But now that we're like, when we think about how to go through all the things in the object that we want to sanitize, it would be pretty simple relatively if we only had to deal with integers, strings, other primitive types, because then we could do just this, this loop going through the object values. Does anyone want to say why this does not work for our particular problem though? each individual string is immutable, but we can, right, so the string dot replace, if this were JavaScript code, that would be an incorrect line of code, yes. That's not, we can hand wave over that right now. Imagine that we wrote the right code in that line. There's a bigger problem.
Sorry, some of the values might be a list, as you said.
Yeah, this doesn't go into any nested structure. It doesn't, if one of the values is an array, you can't, like string.replace, like it doesn't operate on an array. You need to go inside the array. You need to, just like you need to go inside objects. So the way you do that is you recurse. So let's go step by step through how we would make some code to do that. So the base cases are basically what we were already dealing with. If we have a string, that's pretty much the base case. And here, again, the dot replace might need to be a different line of code in a different language. Maybe we need to say object key equals object to replace. I guess that's why they wrote the code like this, because they're making a function replace on the object itself. Yeah, it's pseudocode. We can hand wave around that. And we have separate cases for arrays, where we can iterate through each object and recursively call ourselves on each item in the array. And a similar pattern can be used for objects, where we can go through the values in an object and recursively sanitize those. Does that make sense? And just for super bonus clout, does anyone see any potential bugs with this? I don't think any interviewer would like say this was a failure of a bug, but if we wanted to go for bonus points, we could point out that the keys of an object can also be strings or are strings in JavaScript object notation. And so what should we do if the password is actually one of the object keys? It wasn't actually specified in the problem. So it's not, when things like that are left ambiguous, it's generally bonus points if you can notice that there's an odd corner case to think about. And on the subject of random little details of the language that are interesting to go into, in JavaScript, if you happen to be using that for your language, an array actually is also a type of object. So not having return statements makes this slightly less efficient than it could be. But that's just minor nits. Though I don't think any interview would call you on that kind of stuff. Oh, Luis, you mentioned the primitives such as integers. Since an integer cannot have any characters in it, that is why we are ignoring that case. Sorry, I didn't say that explicitly.
Yeah, that makes sense. Thank you.
Any questions on that question before we move on? Okay, so let's do some pathfinding. Let's say your problem is to navigate a two-dimensional grid. You start in the top left. Am I mirrored? Is this top left? And you can only go, and you're trying to get to the bottom right, trying to go diagonally across this grid. You can only go right or down. That's your only operations. And your input is a 2D array where you either have empty strings indicating a unobstructed cell that you can traverse through, or an asterisk, meaning it is a blocked cell. You cannot use any paths going through that. So for example, here's 3 example cases. Now the top left, we've got a 3x2 grid. The number of paths you can go through there, you can either go all the way right and then down, or down and then all the way right, or right, down, right. There are 3 options. For the example below that, you can go all the way right, then down, all the way down, then right. But that's really all you can do because of the block cell. You got 2. And now that we have that problem statement clear, how do we generalize this to whatever kind of grid? We are going to think recursively. You're getting the habit of picking base cases. I would abstract that as we think from the end back to the beginning. So we can talk about how if you're already at the end item, you know you have exactly 1 path. And then you can look at, well, what are the things next to the end? So cell A, still, you just have 1 path to the end. Cell B, you still have 1 path to the end. And cell C, you can either go to A or you can go to B. Each of those just have 1. So now you have 2. When you look at D, you could go right and go to C. You can't go down because it's blocked. So D has the same number as C. And does anyone want to try to summarize this into a pattern that we can try to code? Yeah, question mark equals x plus y. Assuming you mean the number of paths from x plus the number of paths plus y, absolutely. For each square, number of paths to the end is the sum of the number of paths from your neighbors. We're going to define x and y coordinates as being 0, 0 on the top left. And then this pseudocode should represent that. Now we talked about the base case of being at the last cell. Is that sufficient for covering the base cases? I should be more specific. I will go ahead and say, no, it is not sufficient because we could be off the grid or we could be on an obstacle, in which case there are 0 valid paths. Having a base case like that not only makes our function more resilient to bad inputs, but also enables us to have simpler recursion code. Kind of similar to how we used the none check in the tree symmetry, then we can, it means we only have to do our logic checks in fewer places. How do we know when we're off the grid? So the grid is going to be a 2-dimensional array where we know the lengths, and we can compare our XY position to the lengths of the arrays. So here's what that code could look like. Calling ourselves paths helper, where we get the grid being a 2-dimensional array and a position row and column. So first we're checking, are we on an invalid square with no paths? That can be if our row position, I suppose y, in other words, is more than the length of the top level array, that means we're off the grid. And or if the X position, the column, is more than the nested array, where I think we're assuming that all of the subarrays are the same length. So we can count on the 0, though if we were being very pedantic, we could verify that in some input validation. And we also want to check that we are in an empty square, not an asterisk. Or if we are on an empty square, we're okay. If we're on an asterisk or some other obstacle, we have 0 paths. And then we have the good base case that we've reached the end, where we are at the XY position that matches the full size of the 2-dimensional array, the length of the top level array and the length of the nested array. After we've covered our base cases, we just have to do our recursion, where we call ourselves with shifting 1 to the right and shifting 1 down in position. Does that make sense? Cool. Thank you all for the wonderful feedback in the chat. I appreciate it. Now, the big O for this is a little tricky. And I don't know, if I were an interviewer, I personally would think this was not a great exercise, but a lot of interviews really love to throw some crazy big O analysis at you. So just for the purpose of practice, figured maybe we can talk through this. The runtime of this, it's going to work out to be the work you're doing, since you're going through every possible path, it's going to be proportionate to how many paths there are. So we want some way to say how many paths there are as a function of our inputs. Now, for the sake of simplifying our eventual answer, let's say our grid is n+1 wide and n+1 tall. Does anyone want to take a stab at how many paths there will be through such a grid? The hint I can give you is the way I would think of it. Interesting. Where are you getting your numbers 8, 2, and 4 from? Oh, for this particular case. I see. I think you're almost exactly right, I think. Right, to talk through it, yeah, you have studied combinatorics, good work. I think of this as you are defining a sequence of m downs and n rights to traverse this grid, and that frames it in a more in a way that combinatorics is more familiar with dealing with, where you have when you have a sequence of m plus n items and you are choosing where to put those n's, you are dealing with m plus n factorial over m factorial times n factorial. That is not something any interviewer would expect you to come up with on the fly, but it would be pretty cool if you were familiar with combinatorics to show that off, or if you could at least identify, oh, this is going to be some factorial type complexity because we're dealing with permutations of sequences. yeah, so you were basically right on that. Now, you may be noticing that a lot of these algorithms have some pretty poor complexities. So now we're going to talk about how we can do recursion in a smart way to not have nearly as many downsides in performance. So let's talk more about the space that we take up with all of those function calls. Something pretty intrinsic to how we described recursion. It turns out there is a trick you can do sometimes. If you can structure your function slightly differently, it's probably not apparent why this version of factorial is significantly different than our original version of factorial. We're complicating the function definition by passing in this optional parameter result. But what this enables us to do is the recursive call to ourselves is now the absolute last thing that the function is doing. And your compiler knows that, or your runtime knows that. And if it's a smart compiler, maybe it can, instead of making a new frame on your call stack for this function call, maybe it can replace your current one. This is called tail recursion. And if your environment supports it, then you can get back to a constant time space with your recursive calls. Not everything supports this. I think every compiled language probably does, but I was just checking into what JavaScript support for this currently is. Apparently Safari's runtime does support this, but Chrome's doesn't yet. So your mileage may vary, but this is a very classic trick for making recursion more performant. Another thing you can do sometimes, and this is not specific to recursion, anytime you have a whole ton of processing work to do, you should think about whether you can leverage the fact that computers have more than one processor nowadays. Single threading is going to be a bottleneck in a lot of cases. So recursion being spreading out function calls could be a natural fit for taking advantage of multiple threads. It only makes sense if there's a lot of work to do because the overhead per thread is generally pretty high. And if your functions are ever referring to the same state, if they are trying to communicate with each other in any way, any sort of coordination, that is a whole rat's nest of trying to get multiple threads processes to be communicating and coordinating. That is a whole lesson in itself. I would advise stepping carefully around that. So, and the last optimization I want to talk about is how we talked about how when we have the Fibonacci branching, that we've got basically 2 to the n executions that we're dealing with. Oh, sorry, there was a question. Okay, 2 questions. I'm sorry. Overhead. So overhead is just the general concept of the built-in performance penalties of taking an action. So like before, like when you talk about the overhead of spinning up another thread, another process, like that takes work at the operating system level and every level between you and the operating system. That like there's overhead in calling a function, like calling a function you're adding to the stack. That's the overhead of it. That's a very small overhead. The asking the operating system to create another process, for example, is a very expensive cost. And so that's why we talk about the overhead more in situations like that. So how is exactly recursive? How do you distribute threads and processes across processors? That is going to depend on your language and environment. Some languages are going to be much better at this than others. Like if you've taken a look at Go, they make a lot of choices in how they design the language to take advantage of multiple processors. There's always a way to manually do this, and generally the programmer will say when this should happen. But to give you in practice suggestions of how to go about doing it, I think I would refer you to more documentation of your specific language. Skipped ahead, sorry. Right, so you may have noticed when we were talking about the Fibonacci example earlier, how we are executing the same function over and over. And that was kind of silly. So we could have cached the results from the first time we hit f of 2, right? Like when we're doing our recursive calls, we're calling n-1 before n-2. So that keeps going down recursively. We hit this function call of f of 2 first before this call of f of 2. And we hit this f of 3 before we hit this f of 3. If we could cache the results, then we can cut out entire subtrees, like huge subtrees if this is a big number. The technical term for this is memoization. And it would be a big improvement to most of the examples we've talked about. It wouldn't apply to where we were mutating the object when we were sanitizing the JSON object. That's not trying to return a result, that's trying to process the tree. And so the tree, and there's a larger class of recursion where this is not applicable. You're okay, DP, dynamic programming. Yes, this is a teaser of dynamic programming where I think it's out of scope of this lesson to go deeply into dynamic programming, but this is just such a useful technique from dynamic programming. I felt like it was important to include it. So dynamic programming, it only applies to certain types of recursive problems. So I'm curious if anyone can describe what is other examples of when a memoization would not be appropriate. Right, when does this technique not help you? Totally understandable to not get it. I don't know how much y'all have worked with other kinds of recursive algorithms like sorting algorithms, merge sort, quick sort. Those are not repeating the same executions. In the technical term of art is overlapping subproblems. There's not a lot to cache in those kinds of recursion. So sometimes this helps a lot, sometimes it doesn't. Here's an example of what that might look like in code, where we have this variable, the state, outside of the function call that is keeping track of this cache of results. We can leverage that to actually define our base cases for us. enabling us to have our base case just be check the cache. If our parameter is already in our previous results, just return the previous result of that. Otherwise, recurse as we normally do and set the result in the cache. So we've said that this is going to be significantly better performance. Would anyone like to guess what the new time complexity of this would be? Yes, Luis, it is order n. We have fixed the problem at the cost of a small bit of space usage for this cache. We have fixed our time complexity problem with recursion. And that is why we didn't call out time complexity as a significant general problem with recursion. It's often fixable, or at least able to be get very close to iteration. Now, the last caveat I'll have about memoization is that this is relevant to pure functions. This is why it's not that appropriate to no, never mind what I was saying there. But the point is, if you have some other state that is getting changed by this function, or if the behavior of your function depends on some other state that is not self-contained, basically, if there's anything that could ever make the input and output not for any given input have the exact same output, if that's ever not true, then you do not have a cacheable function. You do not have a pure function. Also, if there's any side effects that executing your function wants to kick off. For example, I don't know, maybe you're writing some code in JavaScript in a browser and you have some side effect of adding an event listener to some part of the DOM. That's a side effect. And if you're returning a cached result instead of executing your function, all of a sudden, whether or not your side effect executes is not guaranteed. So this is getting, deeper into the world of dynamic programming. I don't expect you to deeply understand these nuances and caveats right now, but I wanted to introduce you to the terms and a couple examples so that you would be able to dig deeper when you notice things like this popping up in your situations. And now that we've talked about how to do recursion, let's talk just a minute about what patterns can you look for to notice when recursion is the way you should be thinking about a problem. So you may notice we've talked a lot about trees. Trees are very natural fits with recursion. So we talked about the tree balancing problem first. That's just a tree traversal. Same with the JSON sanitization. That was also traversing a tree. Likewise, if you're going through a file system, nesting into the directories, or if you are making a plugin to your build system that formats code, all of these are traversing structured trees. Now, it's not just taking trees as input. If trees are your output, you probably also want to think about recursion, like parsing. You might be trying to take text JSON and turn it into a JSON object. You may want to be writing your own compiler if you like pain. You might be handling HTML, like user input HTML, and making it safe to display to end users. Like HTML is, you do not want to let hackers put in whatever HTML that you want into your inputs. you need to be very careful with how you display that. So parsing it and sanitizing that I've seen that come up many times. Even just like a 3D game, the way that they analyze the space for what is visible when and what collides with what, like it generally is going to be partitioning that space in a binary tree of like what is connected to what is visible from what. So trees are everywhere. Think about recursion with trees. We talked about sorting. Like not every sort uses recursion, but it's a place that it comes up. And when you have sorted lists, that enables a large set of recursion on the sorted lists. Maybe you're familiar with binary search. That is a classic. You are recursing, dividing and conquering across your list. And the last large class of problems I wanted to whet your appetite with is when you have maybe a way to classify all this as puzzles. If you are trying to figure out a solution where you're assembling different pieces together, but you might hit a dead end and need to backtrack. This is like backtracking algorithms is a term you can search more on, but basically it's a decision tree. And the way we handle trees is we recurse. So this is how you might solve puzzles like Sudoku. This is a good way to decide how to color a map without bordering colors. And pathfinding, as we discussed earlier. Yeah, this is a whole set of things that can be reduced to trees. So y'all already called me out on dynamic programming. That is a great area to dig more into. I really, I did not do it justice in my half-hearted attempt to explain it. I was just trying to introduce what I think of as the most useful technique from it, the memoization. There's definitely more to learn there. And if you want some practice with recursive programming, which as Aditya said, is probably going to be useful in some interviews, here's some lead code problems you can work on. Yeah, questions?
Awesome. Well, folks, think of questions. Just want to say a big thank you to Patrick and Aditya for spending your time on this Sunday explaining these concepts. We know your time is super valuable. So yeah, really grateful that you spend this time. And thank you all of the fellows for participating and spending this Sunday learning some really gnarly concepts. So definitely reach out to your mentors or anyone in the group if you have further questions. But yeah, floor is open for any questions. And otherwise we can wrap. I'll give folks a few minutes. Cool. Well, yeah, thank you so much to the both of you. This was awesome. So yeah.
I hope we didn't go too long.
Definitely not. Right on time. Right on time.
Great.
Cool. All right. And yeah, fellows, definitely leave feedback on the Slack channel if there's anything we can improve on, whether you want things to be more interactive or whatever. But yeah, this is really awesome. And I was happy to brush up on some of these concepts myself. So great. All right. Enjoy the rest of your Sundays.
Bye, y'all.
Bye-bye.
See you.